Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Okay, let's unpack this. Today, we're taking a deep dive into something incredibly powerful and increasingly relevant for anyone looking to earn their pilot's license, even if you're focused on the private pilot license right now, turbine engines. We've gathered some fantastic resources to sort of demystify these incredible power plants so you can understand what makes them fly and, what makes them different. The skies are seeing more and more smaller turbine-powered aircraft like very light jets, VLJs, and microjets, too.
That's right.
So even if you start in a piston-powered trainer, this knowledge isn't just for the commercial guys anymore. It's becoming super pertinent for you as a student pilot looking ahead.
It really is.
Yeah.
What's truly significant here, I think, is that even as a student pilot, just understanding the fundamentals of turbine engines, well, it can give you a remarkable edge.
Right.
You might not be flying one tomorrow, sure, but being aware of their operational principles really prepares you for the broader aviation world. So our mission today basically is to break down their types, how they operate, and some crucial considerations, just ensuring you're well-informed for whatever aircraft you might encounter down the road in your aviation journey.
Makes sense.
We'll start with the basic components, the building blocks, and take you all the way through to those critical operational aspects.
Okay, so when we talk about a turbine engine, what are we actually talking about? It sounds complex, maybe a bit intimidating.
It sounds that way, yeah.
Let's break it down into its core parts.
A good idea.
Picture this. You've got, 5 main sections all working together in sequence. First, the air inlet. That's basically the engine's mouth where air just rushes in.
Right.
Then that air hits the compressor, and it does exactly what it sounds like. It squeezes, pressurizes that air a lot.
Dramatically increases the pressure, yeah.
After that, we move into the combustion chambers. This is where the action happens, right? Fuel gets injected, ignited in that super compressed air.
Exactly. Big heat release.
Creates these hot, expanding gases that then hit the turbine section, which is basically a series of fan-like blades spun by those powerful gases.
Precisely. Extracts energy from the gas flow.
And finally, those gases shoot out through the exhaust. That's what generates the thrust. So the fundamental principle is all about producing incredible thrust by dramatically increasing the velocity of the air flowing through the engine.
That's the heart of it.
It's essentially a very sophisticated air pump and a controlled explosion, wouldn't you say?
That's a great way to put it. It is a sophisticated air pump, a real marvel of engineering.
Okay. And
the big advantages for pilots are pretty clear. They run incredibly smoothly, much less vibration than pistons. They offer a fantastic power-to-weight ratio, so lots of power for relatively little engine weight.
Which is huge in aviation.
Absolutely.
Yeah.
And they efficiently use readily available jet fuel, Jet A, typically. Historically, these engines were way too expensive for small aircraft. But recent advancements, new materials, better designs, they've made them viable for those smaller, lighter production aircraft.
Like the VLJ, as you mentioned.
Exactly. VLJs and microjets, typically seating, 3 to 7 passengers?
Yeah.
This accessibility is precisely why you, as a student pilot, need to know about them now.
And drilling down on that compressor you mentioned, that seems so key to the whole process. I understand there are actually different ways these engines compress the air.
Absolutely. The compressor section is vital, and there are basically 3 main types, each with its own approach.
Okay.
You have centrifugal flow. This one accelerates air outward, sort of perpendicular to the engine's center line.
Yeah.
Think like a centrifugal pump throwing water outwards.
Gotcha.
Then there's axial flow. This uses a series of rotating and stationary airfoils. Think of many small fans stacked in a row.
Okay.
They push the air backwards, parallel to the engine's axis, compressing it stage by stage.
Right.
And finally, some engines use a centrifugal axial flow design. It's clever, really. Combines both types to get the most efficient compression possible for that specific engine.
Interesting.
Knowing these basics just helps you visualize how that initial air gets prepared for the main event in the combustion chamber.
Okay, here's where it gets really interesting, I think, especially for a student pilot. Because not all turbine engines are created equal.
Right. At all.
The way they produce power, how the air moves through them, it leads to 4 distinct types.
That's right.
Let's look at each one because understanding their differences is absolutely key to understanding the aircraft they power.
Definitely.
The most basic of these is the turbojet. Tell us about its foundational design.
Okay, the turbojet is, like you said, the simplest form. It really just has those core sections we talked about. Compressor, combustion chamber, turbine, and exhaust.
Oh, okay.
The compressor squeezes the air, pushes it into the combustion chamber, fuel's ignited, and the expanding hot gas drives the turbine.
And the turbine drives the compressor.
Exactly. It's connected by a shaft, keeps the whole cycle going. Then almost all the remaining energy in those hot gases shoots out the back as high-velocity exhaust.
And that's the thrust.
That is the thrust. It's a pure jet. Very straightforward application of the principle.
So it sounds powerful, simple, but every design has its trade-offs. What are the limitations of turbojets that a pilot should be aware of?
Good question. Turbojets, well, powerful, yeah, they do have limitations. They can be less fuel efficient, especially at lower altitudes and speeds compared to other types. So range and endurance can be limited.
Right.
Another factor for pilots, they can be a bit slow to respond to throttle changes, especially at low compressor speeds, which, could be critical during takeoff or approach and landing. Need to anticipate power needs.
Okay, makes sense. Next up is the turboprop. You see these on a lot of regional airliners, cargo planes.
Very common, yeah.
This is a turbine engine that actually drives a propeller, but not directly, right? There's a reduction gear.
Exactly. So the hot gases coming out of the combustion chamber drive two turbines. One drives the compressor, like in a turbojet.
Okay.
But there's a second separate turbine, often called a power turbine, that's the one connected via a shaft, to a reduction gearbox.
And the gearbox slows down the rotation for the propeller.
Precisely. Because the turbine core spins incredibly fast, tens of thousands of RPM. A propeller is most efficient at much, much slower speeds.
Maybe a couple thousand RPM.
Yeah, in that ballpark.
Yeah.
So that reduction gearing is absolutely crucial. It's a really clever way to merge the turbine's power with the efficiency of a propeller at certain speeds.
So what are those speeds? Where do they shine?
Well, it's a brilliant compromise, really. Blending aspects of turbojets and even reciprocating engines in some ways, turboprops are generally most efficient at speeds, say, between 250 and 400 miles per hour.
Okay.
And at altitudes typically between 18,000 and maybe 30,000 feet. But here's the kicker, especially relevant if you're flying smaller planes. They perform exceptionally well at the slow airspeeds needed for takeoff and landing. They generate a lot of thrust right from the get-go.
Good for short fields.
Exactly. This makes them quite fuel efficient in those specific flight envelopes, a great balance of speed and short field performance. You'll often find their best fuel economy, their minimum specific fuel consumption, somewhere between 25,000 feet, and the turboprops.
Got it. Okay, then we have the turbofan. This is probably what most people picture when they think of a modern jet engine on, like a Boeing or an Airbus.
Absolutely. The dominant engine type for airliners today.
Turbofans were developed, I gather, to combine some of the best features of both the turbojet and the turboprop.
That was the goal, yeah. Take the high-speed capability of the jet, but improve the fuel efficiency, especially at typical cruise speeds.
And the key feature is that big fan at the front, right? It diverts some air around the engine core.
Exactly. That's the defining characteristic. A large fan at the front sucks in a huge amount of air. Only a portion of that air goes through the core, the compressor, combustion chamber, turbine path.
Okay.
The rest of that air, the majority in high bypass engines, is ducted around the core. It bypasses it.
And that bypass air, what does it do?
It provides several major benefits. First, it generates significant thrust itself, just like a giant ducted propeller, quietly and efficiently. Second, that cooler bypass air helps cool the engine core.
Useful.
And third, when it mixes with the hot exhaust from the core, it actually helps suppress noise. Makes the engine much quieter than a pure turbojet.
Right, quieter airports.
Definitely. So the result is an engine that gives you those turbojet-type cruise speeds, but with significantly lower fuel consumption and less noise.
It sounds like they've solved everything, combining the best of both worlds. Are there any significant drawbacks or compromises to that bypass design that a pilot needs to be aware of?
Well, that's a perceptive question. And while they are incredibly efficient, you're right, no design is completely without compromise. For one, the larger frontal area of a high bypass turbofan does create more aerodynamic drag, especially at very high speeds, compared to a slimmer, pure turbojet.
Makes sense. Bigger engine face.
Right. Also, that big fan and the ducting add weight and mechanical complexity, more parts, more things to maintain.
True.
But honestly, for most commercial and many business jet applications, The massive benefits in fuel efficiency and reduced noise far outweigh these drawbacks.
Yeah.
That bypass stream is so critical, it literally gives the engine its name. We talk about the bypass ratio.
Okay, what's that?
It's a key metric. It's simply the ratio of the air to the mass of air that goes through the core.
So a high bypass ratio means most of the air goes around.
Exactly. Modern airliners have very high bypass ratios, maybe 10.1 or even higher. Lots of bypass air for thrust and efficiency.
Wow.
But here's the real insight, I think. This isn't just a minor improvement. It's the fundamental reason modern airliners can fly thousands of miles economically. It's what made long-haul travel accessible.
Right. Changed everything.
It really did. This design significantly improves efficiency for so many modern aircraft you see flying today. They're incredibly common for a very good reason.
Okay. And finally, the fourth type, the turboshaft engine.
Right.
The big difference here, as I understand it, is that it delivers power to a shaft that drives something other than a propeller.
That's the key distinction. Unlike a turbojet where almost all the energy becomes thrust out the back, or a turboprop where much of it drives a propeller,
Yeah.
in a turboshaft, most of the energy extracted from those expanding hot gases by the turbine section is used to turn a shaft. Very little, if any, direct thrust comes from the exhaust itself.
So where does that shaft power go? What does it drive?
Well, expanding on that, the versatility of turboshaft engines is pretty remarkable. The most common application you'll see, helicopters.
Ah, okay. Driving the rotors.
Exactly. The turboshaft engine's output shaft drives the main rotor and tail rotor systems through complex gearboxes.
Makes sense. Lots of power needed there.
Absolutely. They're also widely used as auxiliary power units, or APUs, on larger aircraft.
Right, the APU. You hear that whine on the ground sometimes.
Yeah, that little turbine engine, usually in the tail cone, provides electrical power and bleed air for air conditioning an engine starting when the main engines are off.
So they're kind of the unsung heroes.
You could say that. They're the silent workhorses behind the scenes in many applications.
Yeah.
Very important engines.
Okay, fascinating. So for student pilots, understanding what the cockpit gauges are telling you is, well, it's paramount.
Absolutely fundamental.
And while some instruments are common between turbines and pistons, oil pressure, oil temp, maybe fuel flow,
Sure, those are pretty universal.
turbine engines have some unique indicators that you absolutely need to know about. Let's break those down.
Let's do it. It's crucial stuff. First up, the engine pressure ratio gauge, or EPR.
EPR.
This is primarily used to indicate the power output of turbojet and turbofan engines.
How does it measure power?
Simply put, it measures the ratio of the pressure leaving the turbine section to the pressure entering the compressor inlet.
So a ratio of outlet pressure to inlet pressure.
Exactly. It gives you a direct indication of how much work the engine is doing on the air, which correlates directly to thrust.
Ah, okay.
What's clever about EPR is that the system automatically compensates for changes in airspeed and altitude.
Right.
Those factors affect inlet pressure, but the ratio gives a consistent thrust indication.
But not temperature.
Right. Changes in ambient temperature do affect engine performance, so EPR readings often need a small correction based on outside air temperature to set a precise target thrust.
So for you as a pilot, it's really about seeing the thrust you're commanding, not just how fast the engine is spinning.
Precisely. It's a direct measure of output.
Okay, next gauge.
Next, we have exhaust gas temperature, or EGT. This is probably the most critical temperature instrument on a turbine engine.
Why is it so critical?
Because the temperature of the turbine section, especially the first stage turbine blades right behind the combustion chamber, is usually the absolute limiting factor in how much power you can get out of the engine.
Too hot and things melt.
Essentially, yes. Overheating can cause rapid and severe damage to those very expensive turbine components. So EGT is a hard operating limit. You monitor it constantly, especially during start and high power settings.
Okay.
You might also see variations in the name depending on where the temperature sensors are located. Could be TIT, turbine inlet temperature, TOT, turbine outlet temperature, ITT, interstage turbine temperature, or TGT, turbine gas temperature.
Different acronyms, same basic idea.
Same fundamental idea,
Uh-huh.
measuring the temperature in that critical hot section. The key takeaway here is that temperature is often the ultimate limiter in a turbine engine's operation. This gauge is your lifeline for engine health.
Got it. What else is unique?
Then there's the torque meter. This is how you measure the power output specifically on turboprop and turboshaft engines.
Because they're delivering power to a shaft, right?
Exactly. Torque is simply a measure of twisting force. The torquemeter measures that twisting force being applied to the output shaft that drives the propeller, or the helicopter rotor gearbox.
How is it displayed?
It can be calibrated in various units, sometimes percentage units, sometimes actual foot-pounds or newton meters of torque, sometimes even related pressure units like psi in some hydraulic systems.
But it's basically the horsepower gauge for those shaft-driven turbines.
That's a perfect way to think about it. It tells you how much work the engine is delivering to the shaft.
Okay. And there's one more set, right? N1 and N2.
Yes. The N1 and N2 indicators. These are rotational speed indicators, but they're a bit different than just the single RPM gauge you see in most piston trainers.
Oh, so?
Most larger turbine engines have two main rotating assemblies, or spools, that spin independently on concentric shafts.
Two spools. Okay.
There's a low-pressure spool, compressor stages and turbine stages, and a high-pressure spool, different compressor and turbine stages. N1 represents the rotational speed of the low-pressure spool, and N2 represents the rotational speed of the high-pressure spool.
And these are shown as percentages.
Yes, typically shown as a percentage of their maximum design RPM. So 100% N1 means the low-pressure spool is spinning at its maximum rated speed.
Why track both?
Because they tell you different things about the engine state. N1 is often more closely related to thrust on turbofans, while N2 tells you about the core engine speed, which is critical during starts and for monitoring overall health.
So these indicators give you direct insight into the engine's internal core operation.
Exactly. Much more detailed than just a single prop RPM gauge. You're looking right into the heart of the engine's rotating components.
Okay, that makes sense. Very different from a Lycoming or Continental.
Very different, yeah.
Now, let's move to the practical side. What you, as a future pilot, really need to be aware of when operating or even just being around turbine aircraft.
Right, this isn't just theory now.
These are the crucial gotchas, maybe. The things that separate a smooth flight from a potentially critical incident.
Absolutely. These considerations are pretty common across all turbine types and vital for safe operation.
So what's first?
Let's start with those engine temperature limitations again, specifically TIT.
Turbine inlet temperature.
Right. Where do you think the absolute hottest point in the entire engine is?
Got to be right after combustion, before the turbine.
Exactly.
Yeah.
Right at the inlet to the first turbine stage. That's TIT. And because materials have temperature limits, TIT is very often the ultimate limiting factor in how much power an engine can produce continuously.
So exceeding that, very bad news.
Very bad. It can lead to severe, even catastrophic damage to the turbine blades. It's
Yeah.
like the absolute red line in your car's engine. But the consequences of exceeding it are far more immediate and dire in a turbine. You just don't push it.
Okay. What's another key operational point?
Thrust variations. How thrust changes with conditions. Turbine engine thrust varies directly with air density, meaning as air density decreases, which happens when you climb to higher altitudes, or on hot days when the air is less dense, the thrust your engine can produce also decreases.
So less performance on hot days or high-altitude airports?
Correct. You need to account for that in your performance calculations. It's a key difference to understand, especially comparing it to piston engines regarding humidity.
How does humidity affect them differently?
Well, both types are affected by high humidity, but turbines experience only a negligible loss of thrust, whereas reciprocating engines, piston engines, can see a quite significant loss of brake horsepower on very humid days.
Interesting. So on a really muggy day, the turbine might feel a little stronger relative to a piston.
Relatively speaking, yes. It's less impacted by the water vapor in the air.
Okay. Now, something really crucial, especially on the ground, FOD.
Ah, yes. Foreign object damage. This is a huge concern.
Why is it such a big deal for turbines?
Well, think about that big air inlet we talked about. It's basically a giant vacuum cleaner when the engine's running, especially at high power settings.
Sucking in everything nearby?
Exactly. And what's truly critical here is the constant risk. That seemingly innocent small pebble, a forgotten tool, a bolt, even loose pavement on the ramp or taxiway.
Yeah.
If that gets sucked into the inlet, it becomes like a high-speed bullet fired into those delicate, fast-spinning compressor blades.
Ouch.
Ouch is right. Ingestion of debris, from ramp objects to bird strikes, which are a major hazard, or even chunks of ice shedding off the airframe or inlet can cause significant damage. Sometimes even catastrophic destruction of the compressor and turbine sections.
So prevention is key.
Prevention is the highest priority. You'll see things like vortex dissipators on some engines, which disrupt the swirling air near the ground that can lift debris, maybe inlet screens or deflectors on certain types.
And for the pilot?
For the pilot, your pre-flight inspection is absolutely critical, meticulously checking the engine inlet and the area around the aircraft for any potential FOD sources.
Not just kicking the tires.
Not even close. It's not just a checklist item. It's literally about saving your very expensive engine from potential destruction. Vigilance is key.
That really drives home the importance of those walkarounds. Okay, and speaking of things going wrong, I've heard about hot starts and hung starts. They sound pretty serious.
They are serious, and definitely critical abnormal procedures every pilot needs to be aware of. Let's take hot start first.
Okay.
This occurs when the EGT, that exhaust gas temperature we discussed, exceeds the safe limit during the engine start sequence.
What causes that? Too much heat too quickly.
Usually, yes. It's typically caused by either too much fuel being introduced into the combustion chamber before there's enough airflow, or the turbine isn't spinning fast enough, insufficient RPM, to move enough air through. Basically, too much fuel for the air available.
And if you get a hot start?
You have to abort the start immediately, following the procedure. And critically, anytime an engine has experienced a hot start, you must refer to the Aircraft Flight Manual, the AFM or POH. There will be mandatory inspection requirements, potentially maintenance, before the aircraft can fly again. You can't just shrug it off.
Right. Safety first. What about a hung start?
A hung start, sometimes called a false start, is when the engine lights off, you get combustion, but it fails to accelerate to the proper idle speed. It just sort of hangs at a lower RPM.
Why would that happen?
Could be several reasons. Maybe an insufficient power source for the starter motor, so it can't spin the engine fast enough. Or it could be a malfunction in the fuel control unit, not delivering the right amount of fuel for acceleration.
And the action is similar. Abort.
Yes, abort the start according to procedure. Both of these hot starts and hung starts require immediate pilot action and usually subsequent maintenance attention. It really highlights why monitoring your engine instruments so closely during startup is incredibly important.
Definitely sounds like it. Okay, what else can go wrong?
Then we have compressor stalls. This is an aerodynamic issue within the engine itself.
It's like stalling an aircraft wing.
Exactly the same principle. Imagine those hundreds of compressor blades inside the engine. Each one is essentially a tiny airfoil, a wing.
Okay.
And just like an aircraft wing, they have an angle of attack relative to the incoming air. If that angle of attack becomes too high, the airflow separates and the blade stalls.
What causes the angle of attack to get too high inside the engine?
It usually happens when there's an imbalance between the velocity of the air coming into the compressor stage and the rotational speed of the compressor blades themselves. Maybe the engine ingested turbulent air, or during rapid throttle movements, or even operating outside the designed envelope.
When the blades stall.
When this happens, the smooth flow of air through the compressor is interrupted. You get turbulence, pressure fluctuations start bouncing around inside, the airflow can slow down, stagnate, and in a severe stall, it can even momentarily reverse direction.
Air flowing the wrong way through the engine. That sounds bad.
It is bad. How it manifests depends on the severity. You might get a transient stall, which is often heard as an intermittent bang or pop from the engine as the flow briefly reverses. These might self-correct.
Okay.
But if the stall becomes steady, you'll likely feel strong vibrations, hear a loud roaring noise, see fluctuations in RPM, and usually a rapid increase in EGT because the airflow cooling the turbine is disrupted.
Can that damage the engine?
While most brief transient stalls might not cause immediate harm, a sustained, steady-state stall absolutely can cause severe engine damage very quickly due to the vibration and overheating.
So what's the recovery?
Recovery generally involves quickly reducing the engine power, moving the throttle back, decreasing the aircraft's angle of attack if possible to smooth the airflow into the inlet, and trying to increase airspeed. The specific procedure is critical and found in the AFM-POH.
Are modern engines prone to this?
All gas turbine engines can theoretically stall, but modern designs have become incredibly sophisticated at preventing it. They often have things like variable inlet guide vanes, VIGVs, and variable stator vanes within the compressor that automatically adjust the angle of the blades to maintain smooth airflow across a wide range of conditions.
So less likely now, but still possible.
Exactly. The best prevention is always operating the engine smoothly and within the manufacturer's parameters. Always follow the AFM-POH procedures. But yes, it's a significant safety consideration pilots must be trained for and prepared to handle, as it requires swift, correct action.
Wow. Okay. One more major issue.
Yes, flameout, which is pretty much what it sounds like.
The fire goes out.
Exactly. The unintentional extinction of the fire within the combustion chamber.
How does that happen? Seems like it would want to stay lit.
It usually does, but several things can cause it. You could have a rich flameout if the fuel-air mixture becomes too rich. maybe during a very rapid engine acceleration where the fuel flow increases faster than the airflow can keep up, or if airflow is disrupted.
Too much fuel.
Right. More common, perhaps, is a lean flameout. This happens if the mixture becomes too lean, not enough fuel for the amount of air. This is often associated with low fuel pressure, operating at very low engine speeds for extended periods, especially at high altitude, or throttling back very quickly during descent.
Too little fuel.
Correct. And then, of course, any interruption of the fuel supply can cause a flameout. Flying at unusual attitudes that unport a fuel tank pickup, a fuel control malfunction, flying through severe turbulence or heavy precipitation or icing or, well, simply running out of fuel.
Right. Don't do that.
Please don't. The symptoms of a flameout are typically the same as any other engine failure: loss of thrust, unwinding RPM, falling EGT.
Can you restart it in the air?
Sometimes. If it was caused by a transitory condition like temporary turbulence or icing that is cleared, and you're within the engine's approved air start envelope, specific altitude and airspeed ranges, an air start may be attempted.
But follow the book.
Absolutely. Positively. Always follow the applicable emergency procedures in the AFM-POH. They will give you the exact steps, including the recommended altitude and airspeed conditions, for attempting an air start. It's a critical moment that really tests a pilot's training, procedures knowledge, and discipline.
Okay, that covers a lot of the critical operational stuff. Finally, let us briefly look at how these different engine types, piston, turboprop, turbofan, turbojet, sort of stack up against each other in terms of performance.
Good idea.
This seems especially relevant as you, the listener, think about future aircraft you might fly and understand why certain planes are designed the way they are.
Exactly. It's not about which one is universally best, because they each have their strengths in different regimes.
So how do we compare them, apples and oranges?
Well, we need a few definitions to try and compare them fairly. For reciprocating piston engines, we usually talk about brake horsepower, bhp, the actual power available at the propeller shaft. For turbojets and turbofans, the primary output is net thrust. Sometimes, to compare it to horsepower, we calculate thrust horsepower, THP, which is basically thrust times speed converted to horsepower units.
Right. Power is force times velocity.
Exactly. And for turboprops, since they produce both shaft power and some residual exhaust thrust, we often use equivalent shaft horsepower, ESHP.
What's that?
ESHP is the sum of the shaft horsepower being delivered to the propeller plus the horsepower equivalent of the thrust coming out the exhaust pipe. It's a way to capture the total useful power output.
Got it. So using those ideas, what's the general picture?
Generally speaking, if you look at performance across a range of airspeeds, reciprocating engines, your typical piston engines, excel at lower speeds. They produce good power efficiently down low.
Like in most trainers.
Precisely. Now, as speed increases, turboprops start to outperform piston engines. They maintain their efficiency better as you go faster, up to a point. They actually outperform turbofans for a certain speed range, too. But then, as speeds get higher still, the turbofan really takes over. They become more efficient and produce more effective thrust than turboprops at typical jet cruise speeds.
Right.
So turbofans generally outperform both reciprocating and turboprop engines at those higher subsonic speeds where airliners and business jets fly.
And the turbojet.
The pure turbojet, because it's optimized for very high exhaust velocity, can ultimately achieve the highest maximum speeds, pushing into supersonic flight, though offered at the cost of lower efficiency elsewhere.
So it creates this kind of spectrum of performance.
Exactly. This spectrum shows you why aircraft designers choose specific engine types. It's all about matching the engine's optimal performance characteristics, its best speed range, its fuel efficiency to the aircraft's intended mission profile, and speed.
Makes sense.
For you as a student pilot, understanding this helps conceptualize the incredible diversity of capabilities within aviation. It makes you a much more informed observer of the skies and gives context to the different sounds and shapes you see flying overhead.
So what's the key takeaway from this deep dive today? We've covered a huge amount of ground.
We really have.
From basic components, the different types, those unique instruments, and the critical operational considerations. It seems the takeaway is that while turbine engines might seem complex, grasping these foundational principles, how they work, their limits, doesn't just prepare you for potentially flying advanced aircraft someday.
Right.
It fundamentally shifts your understanding of flight itself, doesn't it?
I think it does. You've now got a really solid foundation for understanding these incredibly powerful and efficient machines, especially as they continue to reshape the future, even for smaller aircraft.
Yeah.
Knowledge is most valuable when it's understood and then applied.
Yeah.
As you continue your flight training, thinking about maybe getting your instrument rating or commercial license, this deep dive provides a crucial lens. A way to understand not just how aircraft fly, but why specific engine choices are made for different roles, and the unique demands those engines place on the pilots operating them. And maybe this raises an important question for you to consider looking forward. Given the rapid advancements we're constantly seeing in aerospace materials, controls, and efficiency, how might the next generation of, say, very light jets, or even smaller turbine aircraft, powered by ever more advanced engines, continue to reshape the pathways and possibilities for pilots like you?
Interesting thought.
And maybe even more intriguingly, what new operational considerations or challenges might emerge with those future technologies that we haven't even really thought of yet?
Food for thought, definitely.
Keep that curiosity burning, keep learning, and happy flying.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.